Welcome. Physical AI is a machine that senses the world, understands it, reasons, and acts. Today, we open up the middle of that loop because something sits in there now that did not exist 3 years ago. Here is the loop: sense, understand, reason, act forever. For years, each stage was a separate system, hand-wired to the next. Understanding was one model, reasoning another, control a third. The last 3 years collapsed those three into one network in 2 steps, and you need both. Start with where we came from. 3 fields developing separately. Vision models could see, but only what they were trained to see. A new class meant a new dataset and a retrain. Language models could read and write fluently about a world they had never perceived. And control systems could move precisely and only in the situation they were engineered for. 6 words will come up a lot, one line each. Multimodal, one model that takes more than one kind of input. Pixels, words, sensor readings. Perception, turning raw signal into an understanding of what is actually there. Grounding, tying a word to the thing it points at in the real scene. A token, the small unit a model reads and predicts, whether that is a word or a joint angle. Autoregressive, generating one step at a time, each conditioned on everything before it. And a policy, the rule from what it sees now to what it does next. Step 1 was to give a language model eyes. That is a vision language model. A vision encoder trained on millions of image and caption pairs so it can associate what it sees with words. A projector, a small stack of layers that turns what the encoder saw into tokens the language model can read. And a language model doing what it already does, taking tokens and producing text. And here is the difference. The old model had a fixed list of classes. This one takes an instruction. Change the prompt, change the task. Which opens the door to almost anything you can ask for in words. Answer questions about a picture. Summarize an hour of video, read handwriting and work the problem out step by step. Parse a document and understand the layout, not just the characters. Point it at live camera feeds and it becomes a watcher. An empty shelf, a stalled machine, water on the floor. One model where you needed a dozen. It gets there in stages. First, alignment. The 3 parts are trained together on image and caption pairs until they agree on what things are. Then instruction, example prompts with the answers you wanted, so it learns how to respond, not just what it sees. Then, optionally, a light pass over your own data to teach it a defect it has never seen. Progress is scored on multiple choice benchmarks, images, charts, documents, video. And then it hits a wall. A vision language model can describe that cup in perfect detail. It cannot pick it up. Its output is text. To move something, you need an output that is motion. So step 2, keep the eyes and the language and add a third thing, actions. In, what the camera sees, what you asked for in plain language, and where the robot's own body is right now. Out, the next move, not a description of it, the move itself. One network, one set of weights, doing perception, grounding, and control together. How? With a trick that is almost embarrassingly simple. A language model turns text into tokens and predicts the next one. So turn the robot into tokens too, and the sentence it generates is the motion. 3 kinds go into the stream. Prefix tokens carry the context, the scene from the camera and the instruction. Stack the green blocks on the red tray. State tokens carry the body, joint angles, gripper, open or closed, force on the fingertips, and on a mobile robot where it is on its map. Action tokens carry the future, the next joint change, the next wheel velocity, the next grip. At runtime, it decodes those action tokens autoregressively, each one conditioned on the scene, the instruction, and every move already made. The same machinery that writes a sentence writes a trajectory. Here is one step concretely. A camera frame goes through the vision encoder and becomes roughly 400 tokens. The instruction goes through the language side and becomes about a dozen more. The joint angles go through a small network and become one compact state vector. Cross-attention fuses all 3 into one representation, and a decoder turns that into around 50 action tokens, which become motor commands. Then the loop closes, the commands execute, the sensors report back, and the state tokens update. So if the wind moves the apple mid-reach, it does not fail. It rereads the scene and adjusts the grasp. That is the difference between a plan and a policy. A plan is written once. A policy is rewritten every few milliseconds. Where does the skill come from? Two very different pools. Web-scale image and language data gives it meaning. What an apple is, what ripe means, what a handle is for. Robot trajectory data gives it consequences, demonstrations real or simulated from many different machines. Training on both beat scale. 7 billion parameters fed this way outperformed a 55 billion parameter rival on real robot tasks. The designs cluster into three families. Early fusion merges vision and language at the input and freezes the backbone, so the model keeps what it knew and only a small action head learns the new job. Dual system splits fast from slow, a planner taking most of a second to turn clean the table into a list of jobs and a controller running every 10 milliseconds to do the gripping. And self-correcting designs add a slower path that wakes only on failure. The grass missed, so diagnose it and try again differently. That cut failures by about a third. There is a newer family, and it is the one to watch. A standard model maps what it sees straight to an action. A reasoning one does something first. It breaks the task into smaller problems and writes out its working where you can read it. The pedestrian is hidden by the truck, so slow before the junction, then turn. You train that with chain of thought tasks and reinforcement learning against rewards you can verify, so the reasoning stays honest rather than merely fluent. And it compounds. What the fleet meets in the field improves the base model, which improves everything built on it. Then two brutal constraints because this has to run on the machine. It has to fit. Freeze the backbone, train a tiny adapter, cut the numeric precision, which keeps about 97% of the success rate, and prune the dead weight. And it has to keep up. One token at a time gets you 3 to 5 decisions a second. An arm needs tens to hundreds. So, compress the actions, a full second of motion as 16 tokens, and decode groups at once instead of one by one. Then compile it for the exact chip it runs on, about 30% less latency, a quarter less energy. So where is this running? Humanoids and factory arms, where you retask a robot by talking to it instead of reprogramming it. Vehicles and drones reading a scene and an instruction together. Take the exit behind the red truck. Operating rooms, where an instruction becomes motion at sub-millimeter precision. Wards, orchards, fields, and city cameras that prioritize what a human should look at. None of it is solved, and it starts with the eyes. Most vision encoders take a small square image. A high-definition frame gets shrunk to fit, and small things vanish. Cutting it into tiles helps, and it is not free. They learn from captions, and captions do not say where things are, so grounding stays vague about exact position. And long video overruns the context. There is a limit to how many frames it can hold at once. Then the acting. Chopping a smooth motion into a few hundred steps is fine for a box, not for a stitch. The smoother alternatives cost 3 times the compute. Collision prediction in clutter runs around 82%, and an emergency stop can take half a second. And on a genuinely new task, performance can fall by 40%. Dim the lights, and vision alone loses 20 to 30. So what does the next version look like? A shared multimodal core trained on interaction, not just pictures and text, so it carries physics and consequence. Skills that transfer between bodies, scores that measure safety and recovery, not just success, and inference that stays on the device because these machines watch rooms people live in. 4 things to carry out of this. A vision language model is an encoder, a projector, and a language model. A vision language action model adds a third thing, and it is motion. Everything becomes a token, including the body and the next move. And the newest ones reason first and show they're working. One network that sees, reads the instruction, and moves. That is what closes the loop. Thanks for watching.